Welcome to this lesson on quantile-quantile plot diagnostics. Imagine you and a friend are running a marathon and you want to know if you both run at the exact same pace. If you plot your times at every mile marker against each other, identical pacing would form a perfectly straight diagonal line. A QQ plot does exactly this, but instead of comparing two runners, it compares your actual data to a perfect mathematical model. Let us dive in and see how this works. Now that we understand the basic idea, let us look at what a QQ plot actually measures. In linear models, we want our model's errors, known as residuals, to follow a perfect bell curve. A residual is simply how far off the model's guess was from reality. To check this, we calculate the quantiles of both our actual residuals and the theoretical bell curve. A quantile is just a cutoff point that divides sorted data into equal fractions. By plotting these against each other, we visually test the assumption of normality. If the errors are truly normal, the points will tightly hug a straight diagonal line. Before we can plot anything, we must organize our data. This first formula represents the sorting of our actual observed residuals. We arrange them in order from the smallest, most negative error to the largest, most positive error. The symbol EI represents the sorted values, while N is the total number of data points. Sorting the data is the mandatory first step because quantiles are based on the rank or position of a value within the entire dataset. As the total number of data points n increases, we get a smoother and more reliable diagnostic plot, giving us a much clearer picture of the model's behavior. With our data sorted, we move to the next step. This formula calculates the cumulative probability for each sorted data point. The symbol pi represents this probability, based on the rank I and the total count n. Notice the subtraction of 0.5. This is a small mathematical adjustment called a continuity correction. We subtract it to avoid calculating a probability of exactly 100% for the final point, which is mathematically impossible to plot on an infinite bell curve. As the rank increases, the cumulative probability grows closer to 1. Now, we need to find where these probabilities live on a perfect bell curve. This formula finds the theoretical quantile from the standard normal distribution. In plain English, this formula asks the mathematical question, what exact value on a perfect bell curve gives me this specific probability? The symbol Zi is the theoretical z-score, which acts as our horizontal coordinate on the plot. The symbol phi inverse represents the inverse cumulative distribution function. By pairing the actual sorted residual with this theoretical value, we create the exact coordinates needed for our QQ plot to visually test our model. Let us see this process in action with a concrete example. We have a simple linear model with 5 residuals. Our first task is to find the coordinates for the QQ plot to check if these errors follow a normal distribution. We start by sorting the raw residuals from smallest to largest. These sorted values represent the actual errors our model made, and they will serve as the vertical y-coordinates on our final diagnostic plot. Sorting them is the crucial first step to finding their quantiles. Continuing with our sorted data, let us look at the first and smallest residual. We calculate its cumulative probability using our formula, which gives us 0.10 or 10%. This means 10% of the data lies at or below this first point. Next, we use a standard normal table to look up the value that corresponds to the bottom 10% of a perfect bell curve. The table tells us this value is approximately negative 1.28. This theoretical number becomes our horizontal x-coordinate. Finally, skipping ahead to the largest residual, where the rank is 5, we repeat the probability calculation. The formula yields 0.90, meaning this point represents the 90th percentile of our dataset. The theoretical value for the 90th percentile on a perfect bell curve is 1.28. This gives us our final plotting pair for the highest value. If we plot these points and they form a straight diagonal line, it physically means our model's errors are perfectly normal. Now that we know how to build a QQ plot, what happens when the data is not perfectly normal? When the data violates this assumption, the dots deviate from the straight line in specific recognizable patterns. Learning to read these patterns is exactly like reading an X-ray. Tail problems create an S-curve shape. Heavy tails mean there are far more extreme outliers than expected, while light tails mean the data is too tightly clustered. Skewness creates a one-sided curve, often looking like a U or J shape, indicating a long tail stretching into positive or negative numbers. Here we see a visual cheat sheet for diagnosing model errors. The top left panel shows a perfectly normal distribution, hugging the straight diagonal line. On the top right, the heavy tails form a distinct S shape, breaking away at the extremes. On the bottom left, light tails flatten out horizontally. Finally, on the bottom right, we see right-skewed data, forming a U shape that bends upwards. By comparing your actual QQ plot to these 4 standard panels, you can instantly identify the exact nature of the error in your data. Let us look closer at the mathematics behind that U shape we just saw for right-skewed data. In a right-skewed dataset, the largest observed residual is significantly greater than what the theoretical normal distribution predicts. The symbol shown means much greater than. The theoretical model expects the highest value to be Zn, but the actual data produces a massive outlier. Meanwhile, the smallest residuals might still closely match the theoretical predictions, meaning the left side behaves exactly as expected. The problem is entirely isolated to the unusually large positive errors. Let us apply this mathematical mismatch to a real-world scenario. A researcher fits a linear model to predict house prices. The model produces residuals that are mostly small and negative, but a few are extremely large and positive. We need to understand how this will manifest visually on a QQ plot. We will analyze the relationship between the theoretical quantiles and the observed residuals for this right-skewed distribution, comparing the high percentile theoretical values with the corresponding observed residuals. Continuing our analysis, because the highest values are much larger than expected, the points on the far right of the QQ plot will shoot upwards. They break away from the 45-degree reference line, creating the classic U shape associated with right-skewed data. This visual cue immediately warns the researcher that the normality assumption has failed. Physically, this means the model cannot be trusted as is. The researcher must now apply a mathematical transformation, like taking the logarithm of the house prices, to fix this skewness before trusting the model's predictions. So, why does all of this matter in the real world? In linear regression, all of our statistical tests, like checking if a variable is significant or building confidence intervals, rely heavily on the assumption that the errors follow a normal bell curve. If this assumption is violated, our calculated probabilities become untrustworthy, and our confidence intervals might be completely wrong. The QQ plot is the most reliable, universally used visual tool to check this assumption because it provides a clear, objective line to evaluate, unlike a simple histogram. Let us review the key takeaways from our lesson. A quantile-quantile plot is a powerful visual diagnostic tool that compares observed residuals against expected theoretical values. By plotting these points, we can instantly see if our model's assumptions hold true. A straight diagonal line means the assumptions are perfectly met. Specific curves like S-shapes for heavy tails or U-shapes for skewness tell us exactly how the data deviates. Mastering the QQ plot allows you to confidently diagnose and correct underlying issues in any linear model. Great job following along.